10.2 is on page 685, talks about graph terminology and special types of graphs. We're going to pick out of this what we need for now, and we will come back and pick the rest later. So we have few definitions out here. Definition 1 talks about two vertices u and v in an undirected graph G are called adjacent or neighbors in G if u and v are endpoints to an edge E of G, which means they're connected by an edge. Such an edge E is called incident with the vertice U, and V and E is said to connect U and V. Okay, when I do examples, I'll point those out. The degree of a vertex is an undirected graph. In an undirected graph is the number of edges incident with it. Except for loops, they double. Except that a loop with a vertex contributes twice the degree of a vertex. So anytime you see a loop, you double the degree. The degree of a vertex V is denoted by degree of V. A vertex of degree 0 is called isolated. That doesn't connect to anything. It follows that an isolated vertex is not adjacent to any vector because there is no edge connecting it to anything else. Vertex G in graph G in example 1, you could look at it, is isolated. They have a graph. Now I want the second part. So this part really doesn't really apply, but I wanted to point this out of the book. A vertex is pendant if and only if it has a degree of 1. Consequently, a pendant vertex is adjacent to exactly one other vertex. If I have an undirected graph with m edges, then the sum of the degree is going to be 2 times the number of edges. So the degree of V will be 2 times the number of edges. This is one way to figure out how many vertices you have. Note that this applies even if multiple edges and loops are present. When u and v is an edge of a graph with directed edges, u is said to be adjacent to v, and v is said to be adjacent to u. This is if it's directed. The vertex u is called the initial, and v is called the terminal. So kind of like beginning and end. The initial vertex and terminal vertex of a loop are the same. So a loop takes you back to where you were. Now this notation, again, we have an example on that. In a graph with a directed edge, the n degree of a vertex V denoted by degree minus, that's n, is the number of edges with V as their terminal point, meaning they're coming into it. The out degree of V denoted by degree plus, this will be like taking V to be the initial. You start there and you head out toward another vertex. Note that a loop at a vertex contributes 1 to both the in and the out, so it counts for coming in and going out. And in any graph with a directed edges, the degree of in must equal the degree of out, and that's going to equal the absolute value, the number of edges. So let's get this to work. This is on page 699. So it says, find the number of vertices. Well, how many vertices do we have in this diagram? We have A, B, C, D, E. We have 5 vertices. The number of edges, well, let's see how many edges we have. No, not that one. Let me count that one last. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 edges. What is the degree? Well, here, degree of A, degree of B, degree of C, degree of D and degree of E. So degree of A, that would be specifically for A. 1, 2, 3, 4, and this counts as 2. Remember, that's 6. For B, 1, 2, 3, 4, 5, 6 as well. Degree of C, where's C? Right there. 2, 3, 4, 5, 6. Degree of D, 1, 2, 3, 4, and 5. And degree of E, 1, 2, 3. And then identify all isolates. We don't have any. Or pendant vertices. All right. Moving on to the next problem. It says find the sum of the degrees of the vertices for each graph in 1 through 3. So I copied them down and verify that it equals twice the number of edges. Well, let's see. If I look at example 1, I'm going to go in order A, B, C, D. So in that order, A, B, C, D, E, and F. A happens to have 2. B has 1, 2, 3, 4. C, 1. D, 0. E, 2 of them. And F2, not 2, 3. And that turns out to be a 12. Isn't that 2 times 6? So how many edges do we have? We have 6 edges. And you can count them if you wish. 1, 2, 3, 4, 5, 6. If I go to the second example, again, A, B, C, D. A has 1, 2, 3, 4, 5, 6. B, 1, 2, 3, 4, 5, 6. C, 2, 3, 4, 5, 6. D, 1, 2, 3, 4, 5. And 3 for E. That turns out to be, what is that, 18, 21, 26. That's 2 times 13. We should have 13 edges. And if you count those, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There you go. So we're going to use this later on. Make sure we grasp this. And here, again, if I go A, B, C, D, A, 1, 2, 3. B, 1, 2 only. C, 1, 2, 3, 4. D has 0. E, 1, 2, 3, 4, 5, 6. G, 1, 2, 3, 4. G, H, 2. And I, 3. That is 9, 19, 20, 24. So that would be 2 times 12. We should have 12 edges. So if I count the edges, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. All right. If I move to 8, it says determine the number of vertices and edges. Okay, number of vertices and edges. Let's see how many vertices we have. A, B, C, D. We have 4 vertices. And how many edges? 1, 2, 3, 4, 5, 6, 7, 8 edges. Okay, we got that part. Determine number. Okay, and then it says find the n. So degree n on A, degree out on A. We want the degree n on B, the degree out on B, and we want the degree in on C, the degree out on C, and we want the degree in on D and the degree out on D. Well, let's see how that works. If we start with the first one, if I look at the degree in on A, inwards 1, 2. Outwards, there's also 2. On B, coming in, the loop is coming in, that's 1, 2, 3. And going out, the loop is 1, 2, 3, 4. If I look at C, coming in is 1, 2 of them. And going out seems there's only 1. And here, since it's a loop, 1 in and 1 out. And that's pretty much how this works. Now, the next problem, they want us to go back and do those one more time, but they're asking for each of the following to determine the sum of the in degrees of the vertices and the sum of the out degrees directly, show that they are both equal. Okay, well, let's see how this works. If I go for the n again, I'm going to go by A, B, C, D in that order. A inwards, 1, 2, 3 for A. B, 1. C, 1. D, oh wait, 1, 2. D, only 1. That would be how many? 3, 4, 5, 6, 7. How about the out? The out would be on A, 1. That's it. On B, going out 1, 2. On C, going out 1. And on D, going 1, 2, 3. That's 3, 4, 5, 6, 7. They are equal. On 8, if I go for N, on A, 1, 2. On B, 1, 2, 3, 3. On C, 1, 2. And on D, only 1. That is 3, 4, 5, 6, 7, 8. If I look for the out, on A, we have 2 going out. On B, we have 1, 2, 3, 4. On C, we have 1 going out. And on D, we have 1 going out, 4, 5, 6, 7, 8. They are equal. And if I go for the last one, again in that order, A, B, C, D, A has, if I go for N, 1, 2 coming in, 3, 4 coming in, 5, 6 coming in. For B, how many are going in? 1. That one's out, only 1. For C, 1, 2, those are all out, that's it, just 2. For D, N, 1, 2, 3, 4. And for E, there's 0. So that is 4, 5, 6, that's 7 and 6, 13 altogether. And if I go for the out, well, if I go for A, I have 1, just 1 going out. For B, I have going out 1, 2, 3, 4, 5. For C, going out 1, 2, 3, 4, 5. For D, going out 1, 2, it looks like that's it. And for E, that's a 0, 10, 12, 13, they're equal. So we have 7 edges, we have 8 edges, and we have 13 edges. And that's pretty much it for now.